Okay, so I've graded the exams, but I can't give them back to you yet because not everybody has taken it. And also because of that, but I can't like talk through it with you in office hours yet. But on Tuesday, I'll have it back for you, along with a bunch of other old stuff that you guys turned in a long time ago, specifically lab stuff. Yes.
Question. So I saw like when you adjusted the threshold for the grades, is there like a sort of like system for that, or because like some of them would have like different point deviations of like between A, B, C.
Yes. So basically, what I did was I took everybody's like raw score in the class, and brought everybody up to a point where the average is an 80. Then I figure out what letter grades people would have based on the normal scale. And then I go back to the original grades and reassign the letter grades based on what everybody had with the curve score. I know that sounds really weird.
Because I was looking, I was like, usually the spread is like kind of like the same, but it was like some of the
It is kind of wonky, yeah.
Okay.
Yes.
My question about the grading was, how are we supposed to know what our actual grade is in class if it's like a letter and not like an actual, like a letter grade and not like an actual number grade?
So the actual number grade in Blackboard is correct.
On my Blackboard, it shows like the number grade. It shows it without the
letter.
Without the curve.
Right. So that's what you're gonna see, the number grade without a curve, which I know is probably kind of low and scary looking. I understand. But then go to the announcement and look at the curve, and it's like a 67 is an A or something like that.
Okay.
And so if the semester were to end right now and you have a 65, that would be a B+, and that's what would go into Self-Service Carolina.
Okay.
Is there gonna be like some type of like extra credit or something? Like anything?
There's not going to be any extra credit, but that curve is going to bring you way, way up. Way up. Yeah. Okay. I know it doesn't feel good. I know that. Okay. So on the bright side, this next chapter, relative to the stuff we've been doing, is fairly straightforward, I think. I think you'll agree.
So this is gonna be the easiest text.
I didn't say that. Okay, so aldehydes and ketones. Okay, let's remind everybody of what these functional groups are. So these are both carbonyls. The C double bond O is the carbonyl group. And both aldehydes and ketones are carbonyls. There's other kinds, and we're going to talk about those in the next chapter. But we're just focused on these two. So what's this one? That's an aldehyde. Yep. And this one is, by process of elimination, a ketone. So in practice, what this looks like is an aldehyde is always on the end of a molecule, and a ketone is always, at least to some extent, in the middle. Of course, it doesn't have to be perfectly in the middle, but we'll look at some examples here. So some common aldehydes. The first one's kind of an anomaly. You guys probably should be familiar with this one. What is that? I know you guys are using it in your other lab courses, probably. Starts with an F. Formaldehyde. Yep. Usually when you have a liquid and it says formaldehyde, it's like 30% or something formaldehyde in water. Formaldehyde's weird. As you can tell, it doesn't have an R group. It just has hydrogens on it. And that means it has some weird reactivity, and we're going to talk just a little bit about it. But just be aware when you see formaldehyde, you can't always say, oh, formaldehyde is an aldehyde, because it says aldehyde in the name, so I can treat it like a regular aldehyde. That doesn't usually work very well. And as you'll notice, a lot of aldehydes that have common names literally have aldehyde in the name. But for other aldehydes that don't, the suffix that gets used is al, as in aldehyde. So if we have this aldehyde, it's got two carbons, the carbonyl carbon and the methyl group carbon. So that's two carbons. What's the prefix for two carbons? Eth. Yeah, like ethanol. So this is eth and nal. This one also actually has a common name. It's acetaldehyde. This is the stuff that builds up in like cooking oil after it gets old. And so when you go to McDonald's and you get nasty old fries, that's part of what is making them so like acrid and sour tasting. It's also toxic, so yes.
Sorry, are you recording this? It's just good for like the test room.
Yes, I am.
Okay.
Absolutely, yes.
Thank you.
Hello, future people watching online. Okay. Yeah, so that's, think nasty fries, I guess. Now I want French fries. Okay, and then another example. Is this one. This is really similar to a molecule that we did in lab, or doing in lab. What's the name of that one? It has a benzene ring on it, so it's benzaldehyde. Okay, so particularly with this one, you can see that the aldehyde is at the end of the molecule, and it has to be that way because you must have a hydrogen attached to the carbonyl carbon for it to be an aldehyde. Okay, so that's aldehydes. So ketones, the suffix for ketones is -one, not one, but -one. So here's a ketone. It's got 3 carbons, 1, 2, 3. So it's propanone. Now, that carbon in the middle is the only carbon that the ketone can be on. Because if the carbonyl group was on this carbon, it's on the end of the molecule. So it's an aldehyde. Same for that case. So usually we would name ketones with the number of the carbon that the carbonyl is on. In this case, it doesn't really matter, so you can call it propanone or 2-propanone. Fortunately, for this specific example, nobody cares because it has a common name, which is, you use it in lab a lot. At the organic waste, acetone. We're going to see a lot of acetone because it's the simplest ketone and it's easy to draw when I'm showing you reactions that happen with other ketones. But one of the things you'll see is that here in lecture we're going to do a lot of really simple molecules, and you guys know this already because you've seen it every chapter. And then you go to the homework and the molecules are bigger. And it's like, what? And you go to the exam and the molecules are bigger. So one of the things that I'm going to try to make sure we do in class when we're doing practice is do slightly larger molecules and get you to identify, okay, what is reacting? Because you can have a giant molecule and say we're talking about aldehydes and ketones. You need to be able to pinpoint where the reactive center is, where the ketone is in the molecule. Okay, so there's acetone. This one, which looks like benzaldehyde, except we've got a methyl group here. This is acetophenone. If you've got two benzene rings on the ketone, that's benzophenone. And then very similar to acetone, is this. So that's 2-butanone. Butanone because it's got 4 carbons. But another way that we sometimes name ketones is just by the alkyl groups that are attached to them. So this ketone has a methyl group on one side and an ethyl group on the other side of the carbonyl carbon, so it's methyl ethyl ketone. The abbreviation for this, it's a pretty commonly used solvent, is MEK. So in the same way, I guess you could call acetone dimethyl ketone, but nobody ever does that. Okay, so we're not going to talk immediately about how to synthesize aldehydes and ketones. We'll get to that at the end if we have a little bit of time. But the nice thing about these molecules is that there's really only one big class of reactions that they can do. And it all stems from the fact that carbonyls, aldehydes and ketones, and other carbonyls that we'll discuss later, are electrophilic at the carbon atom. So the types of reactions that these are going to undergo, generally, are nucleophilic additions. Okay, so as I said, carbonyls are electrophilic at the carbonyl carbon. So there's two ways that we can explain this, and they're really kind of the same, but the first is induction, or the inductive effect. And this is based off of the fact that oxygen is more electronegative than carbon. So if you kind of remember the trend for electronegativity, here's the periodic table, blah, blah, and electronegativity increases as you go toward fluorine. Fluorine is the #1 most electronegative element, and oxygen is kind of up there pretty close to fluorine. So oxygen is a pretty electronegative element, and electronegativity means the willingness or the desire of an element to pull electrons toward itself. And so the inductive effect is just showing that with an arrow and saying, okay, the oxygen is more electronegative, so it wants electrons more than carbon does, and so it's generally going to try and pull some electrons toward itself. That means that the oxygen has more electrons, or more electron density than the carbon. But more importantly, the carbon has some electrons like pulled away from it. So it's lost a little bit of electronness, and it's somewhat more electrophilic, which is kind of like being positively charged. Okay, so induction kind of hand-wavy in that regard, but we can sort of go a step further, and rather than just drawing an induction arrow, we can draw a resonance structure of acetone. So, in this resonance structure, we're essentially going to complete this whole thing where the oxygen is pulling electrons toward itself, and we'll do that by pushing a pair of pi electrons from the double bond up onto the oxygen. So that means we're now going to have 3 lone pairs on the oxygen. When oxygen has 1 bond and 3 lone pairs, that's a negative charge. And we've got to balance that negative charge. In addition, this carbon has had electrons removed from it, so it is now electron deficient, and it's got a positive charge. So resonance is the other method we use to explain how carbonyls are electrophilic at the carbonyl carbon. Right, so that positive charge, well, the carbon with the positive charge is electron poor. And it would really like some electrons. And so, say if you have an incoming reagent that has a lot of electrons, something electron rich or nucleophilic, then it's going to want to react with that carbon atom. The way we draw that is by saying, okay, we start with our carbonyl. If you really like, you could say that, okay, the oxygen has a partial negative charge and the carbon a partial positive charge. It's a lone pair there. And we can take a nucleophile. The nucleophile is electron rich, and nucleophile and electrophile like each other. So the nucleophile is going to attack the carbonyl carbon, and then just like we did in the resonance structure, these electrons move up onto the oxygen. Oxygen is happy to take those because it's electronegative. So we have the nucleophile attached to the carbonyl carbon, single bond to oxygen with 3 lone pairs and a negative charge on the oxygen. Now, what happens after this? Well, a bunch of different things can happen depending on what the nucleophile is, what the reaction conditions are, but this is the start of, I don't want to say every, but basically every nucleophilic addition reaction to a carbonyl does this sort of thing. And yep, so we're taking the nucleophile and we're adding it to the molecule. So nucleophilic addition. Okay, so I showed you an example with a ketone, but this works just as well with an aldehyde. And in fact, it actually works better because aldehydes are more reactive than ketones. Okay. There's two reasons for this. The first is sterics, or steric hindrance, if you like. So let me draw acetone out more explicitly. So there's acetone, and then we'll use acetaldehyde, French fry molecule. Okay, so we're comparing a ketone and aldehyde. So what is the difference in sterics around that carbonyl carbon, which is the electrophilic point in the molecule? Well, in the ketone, we've got two methyl groups. So generally speaking, methyl groups aren't huge by any stretch of the imagination. But in the aldehyde, we've got one methyl group and then just a teeny tiny little hydrogen. So the aldehyde is less sterically hindered. That means there's less crowding around the carbonyl carbon, and when we have a nucleophile like this that comes in, there's less stuff blocking it from getting to the carbonyl carbon, and so the aldehyde is more reactive. Okay, so there's also an electronic argument. When we say electronics in chemistry, we're not talking about circuits and stuff. We're just talking about electron density and resonance structures and movement of electrons and stuff like that. So same molecules. But here for electronics, we're going to kind of go back to induction. We are going to go back to induction. So because the oxygen is more electronegative, it's going to pull electron density up toward itself. And in order to sort of try and compensate for that, some electron density is going to come from this carbon and from this carbon to sort of try and fill the gap that's left by the lack of electrons that have been pulled up by the oxygen. So that happens like this in the ketone. Both of the carbon atoms contribute to sort of kind of fill in that gap. I'm not saying we're trying to form a double bond or anything, but a little bit of electron movement is happening. In the aldehyde, there's still the inductive effect of the oxygen atom, but really only this methyl group is providing any sort of significant induction to help out. The hydrogen atom, it's not really doing anything to help. So the aldehyde is less stabilized by induction. So, if it's less stabilized by induction, that means that the void or the electron deficiency that's caused by the oxygen atom pulling those electrons upwards is not filled or helped out quite as much. And so it's got more electron deficiency, and so it's more electrophilic. And on top of that, the steric argument that we talked about, there's also less stuff in the way for a nucleophile, something that has tons of electron density, to come in and fill that gap. So aldehydes are more reactive than ketones for those two reasons. Questions on that? Cool. Okay, let's talk about, I've mentioned that a nucleophile could possibly react with this, but what do you mean? So there's, we're going to classify these by element because I think that makes it a little bit easier. We're going to start with nucleophiles based on oxygen. Okay. And the best way to show this is by example. So let's take an aldehyde like formaldehyde. And what if we treat this with water and a little bit of an acid catalyst? Doesn't matter what our acid catalyst is, we just say H plus and it's hydrochloric or sulfuric or something, but there's some protons floating around in solution. And this will kind of react. And form this molecule, which is called a hydrate. It's called a hydrate because, well, you could say, all right, well, we're adding water to it. When you add water to yourself, you hydrate yourself, right? So we're adding water to the molecule, and if you look at the specific atoms that are making up each of these molecules, which fortunately is a small molecule, so it's not too difficult. The carbon here and these two hydrogens stay the same. Our one oxygen that's attached to the carbonyl carbon has been replaced, by two oxygens and two hydrogens. So we've added the equivalent of H2O to the molecule, so that's a hydration. This specific reaction is unique in that it's disfavored for all carbonyls except formaldehyde. Now, that's a good thing because in your body, you've got tons of different sorts of ketones, and in nature, there's a bunch of different ketones. Imagine if they just reacted with water. That wouldn't be fantastic. And so if for some reason you make a molecule that has these two OH groups, both attached to the same carbon, but there's not hydrogens here, there's other stuff like methyl groups or something, that molecule will decompose really quickly. So the reverse reaction will happen quite easily here. Now, for the case of formaldehyde, this reaction does happen, and so a solution of formaldehyde has a good amount of this molecule floating around in it as well, but it goes back and forth. Okay, but the main thing here is we're going to see some reactions that look very similar to this, but if water is the nucleophile, oxygen nucleophile, this is only going to work for formaldehyde and not for anything else. Okay, so we can do this same kind of reaction with other carbonyls and with other nucleophiles. So let's look at those. All right, acetone again. In this case, we're going to add an alcohol of some kind. This can be methanol or ethanol or a giant molecule that happens to have an alcohol group on the end of it. Again, we need an acid catalyst for this reaction to happen. And we're really going to do the same thing that we did. So we've attached a hydrogen to the oxygen and then another OH group to the carbonyl carbon. So what we'll do here we do get an OH group, but we also get an OR group. So R can be an alkyl group, it can be a benzene ring or a benzene ring with some other stuff attached to it. We'll see some examples in a moment. But if we add an alcohol to a ketone with an appropriate acid catalyst, you get this molecule which has one O group, one OH, and one OR. This is called a hemiacetal. Hemi means partially, and this is easier to explain when we've seen the next example, but it's called a hemiacetal because only one of the oxygens has an R group on it. Okay, if you just add two equivalents of the same alcohol, rather than getting this product that has two different groups on it, you get that molecule, which has two of the same groups, the OR group. And the only way we can have this, right, is if we have two of the R groups to attach, and so we need two equivalents of the alcohol. This reaction has water as a side product, which is going to be important because it's an equilibrium reaction. And so this reaction may or may not be favored, mostly due to if you've got a ton of water in the solution. Because of Le Chatelier's principle, if you increase the concentration of a reagent on this side, it's going to push the equilibrium that way. So in practice, when you do these reactions, you need to find some sort of way to remove this water side product in order to get the reaction to go the direction you want it to.
In the lab, is that what we're doing with these?
No. We're not going to do one of these reactions in lab. They're fickle. Okay. A hemiacetal has one group with an R. And if you have two groups, well, it's not partially an acetal. It is an acetal. Okay, the easiest way to remember the difference between these two is hydrogen, hemi. If you have a better mnemonic, feel free to use it, but okay, so when we have two alcohols, we get one R group attached to each of the oxygens. But what we can do instead is rather than having two molecules that each have one alcohol, what if we have one molecule that has 2 alcohol groups on it. So this is ethylene glycol. And in the same way that this reagent here is just ROH and ROH, right? Just 2 equivalents of ROH. This molecule, ethylene glycol, has an ROH there and an ROH there. So you're kind of adding 2 equivalents of alcohol because you've got one molecule with 2 alcohols on it. But in this case, the only difference is that the R groups are just connected to each other. So if we do this same reaction, we're going to make an acetal and water. But the only difference between this case and this case is that the R groups are just connected. And so what that means is we're going to have an acetal, but the R groups are going to be connected to each other. So what does that mean? Well, acetal is going to start by looking like that. And then, okay, what's the R group? Well, in between the oxygens, there's 2 carbons. 1, 2. So that means that between these 2 oxygens, there's 2 carbons. So we end up with a 5-membered ring. And this is still an acetal, but if you like, it's a cyclic acetal. And you make water as a side product. This particular reaction is super useful when you're trying to synthesize a large molecule because, say you've got a big molecule and it has a ketone on it, and somewhere else you're trying to do your chemistry on the other side of the molecule, but you've got this ketone, and maybe the ketone is reacting with one of your reagents that you want to use. So you can actually mask this ketone by doing this reaction, almost always with ethylene glycol rather than some other molecule, making this acetal. Then you go back to the other side of your molecule, do some chemistry over there, and then, well, if we take water, add it to this acetal with some acid, then we can push it back the other way, and now you've uncovered your ketone. Those are called protecting groups. We're not really going to talk about them, but that's the main use of this reaction. Okay. So let's do some examples. And so for these, just tell me what the products are. ethanol. And so you can just treat ET as the R. So you don't have to write it out like explicitly, the two carbons, but
Do you want us to just identify or draw a structure?
draw the structure, but also make sure you identify what kind of. Identify first and then draw the structure, I guess. So it's going to be one of these four reactions.
Yes.
Yeah. So for that one, the reagent that you're adding to it only has one alcohol.
Okay.
So it's going to be the second one, where it's just ROH.
Okay.
And the R is those three carbons. Yep, you're just going to attach that to, you're going to make what's a hemiacetal.
Yeah.
Yeah.
No, you're right, you're right. I'm hearing what you're saying.
Yeah, she did say that.
This one's the first one, where the.
Okay.
Double bond.
All right. Okay, so
No, I think what you're saying is right.
for the first one, what's the thought process here? So it's going to be one of these four reaction types. We've got a ketone here. Now, don't get too scared by the 5-membered ring here, because we're just interested in the reactivity of the carbonyl group, the CO double bond. Okay, so what reagent are we adding to it? Well, this is an alcohol, and it's got 3 carbon atoms attached to it. So that looks most like this, because R can be those 3 carbon atoms. So here R, R is these, how should I do that? Here we go. Okay, so we know that we're going to make a hemiacetal. So the best way to start drawing it is to just draw the ketone without the ketone. So in this case, that means just the 5-membered ring. Okay, we know that the reactive center here is the ketone because these methyl groups that are on the example are left alone. And in the same way, this 5-membered ring here is going to be left alone. Okay, so what do we get for the hemiacetal? So we get an OH group and an OR group. All right, the OH, that's always going to be just an OH. And the OR group, all right, so OR, okay, and then R is 3 carbons. 1, 2, 3. Yes.
How do you know that those carbons before the OH are R?
Because
No, you did.
if, so let's see. An R group can be sort of any arrangement of atoms, but the important part is what is the R group attached to? In this case, it's attached to an alcohol. So if we're just looking at the possibilities of these 4 reactions, well, it's not water, right? So we're looking for an alcohol of some kind. It's either going to have 1 OH group or 2 OH groups on the molecule. If it's got 1, then it's got to be ROH, like this. So let's do the next example and see about that. Okay, so for this one here, we have a ketone. It's got some stuff attached to it, but that's okay. It's just going to stay the same. We're just looking at the ketone. All right, so we're adding 2 equivalents of ETOH, which is ethanol. But if you don't know it's ethanol, that's okay. You can still do this problem just fine without knowing exactly what that is, and the acid catalyst. So what does ETOH represent up here? It's not water. It's not ethylene glycol because this has got 2 alcohols on it, and there's only 1 OH group on this molecule.
We're gonna choose OH.
Yes. So here is ethyl. All right, so we've got 2 equivalents of ethanol. And so if we've got 2 equivalents, we're going to make an acetal rather than a hemiacetal. Okay, so first step is to just draw the molecule without the ketone. And we're going to make an acetal. Okay, so that means on this carbon where the ketone was, we're going to have 2 OR groups. So we're going to have an oxygen on each one of those. And then what is our R group? Well, it's ethyl. So if you want, you could draw out 2 carbons because ethyl is 2 carbons. But what it's probably easier to do is just put the ethyl groups there.
Question.
Yes?
So, like the other one, when we had to explicitly draw out the R group, did we have just put OR on the other side?
No. So you would have to so what I could have also written here is PROH for propyl. I don't really expect you to know that. That's okay. But however it's drawn here, you need to draw it the same way there.
Okay.
Yeah.
H2O.
Oh, do you have to? No. Is it helpful? Sure. Good question. Very responsible to draw it, but. All right. So for this one, so we've got a ketone. It's got some stuff attached to it. And we're adding water with an acid catalyst. Okay? So, well, we know what happens when we add water to formaldehyde. You make a hydrate. But this reaction is disfavored for all carbonyls except formaldehyde. This is clearly not formaldehyde. We've got tons of other stuff going on. And so this reaction is not going to be favorable. And so essentially we're going to get no reaction here. Okay, the final one. Another ring. Again, don't let the ring scare you. Here we're adding ethylene glycol. Okay, well this is the same reagent that's here. So that means that our ketone is going to get replaced with this 5-membered ring, including 2 oxygens, a cyclic acetal. So how do we go about drawing that? Well, first thing we want to do is just draw our ketone without the ketone. Okay, so at the point where the ketone was, I'm going to make an acetal, and these oxygens are going to be part of a 5-membered ring. So there we go. So the only difference between this reaction, okay, sorry, plus water, not required, but. So what's the difference between this reaction and the first example? Well, the reagents are exactly the same, ethylene glycol with catalytic acid, but the only difference is the starting material is a 6-membered ring with a ketone, so cyclohexanone, versus just acetone, where you've got methyl groups here. So that means in the products of this reaction, this carbon here has got 2 methyl groups on it. And in this reaction, well, this carbon is 1 out of a 6-membered ring. And in the product, it's also 1 out of a 6-membered ring. So the main recommendation I would have for you is when you're trying to predict the products of these, other than the trick question, just draw, if you're using pencil, just copy the molecule. And then say, okay, what change is going to happen here? Well, it's going to involve the carbonyl. I keep saying ketone. You can do this with aldehydes too. It's going to involve the carbonyl. We're going to have to erase the carbonyl and then turn it into an acetal, whether it's like a regular one or a cyclic one, or a hemiacetal if you've only got 1 equivalent of alcohol. Would you like to see an aldehyde example? Cool. Benzaldehyde. I like benzaldehyde. The only problem with benzaldehyde is it smells like bitter almonds, which you would think would be nice. But the problem is cyanide also smells like bitter almonds. Hydrogen cyanide gas, which is really toxic. And so people have been fired from their research labs by playing pranks where they put benzaldehyde on a hot plate and make people think that there's cyanide in the room. Anyway, don't do that, please. All right, so let's take benzaldehyde and what shall we do? Let's do two equivalents of isopropyl alcohol, isopropanol. Good. And catalytic acid. Okay, so what do we have here? So isopropanol, that's going to be our alcohol. and we have two equivalents of it. So if we've got two equivalents, that means we're going to make an acetal. Okay. So what did I say was the first step? Well, we need to draw the starting material. Just without the carbonyl. The hydrogen's still going to stay there. It's just chilling. And at this point, where the the carbonyl was, our acetal is going to go there. So I have an oxygen, two oxygens attached. Okay, so now we need to put the R group on. So what's the R group in this case? Well, it's everything that's attached to the OH. So it's those three carbons, noting specifically that the attachment is in the middle. So it's an isopropyl group, isopropyl alcohol, isopropyl group. Okay, so what does that look like? Well, one thing you can do is say, all right, the OR is just that, the alcohol without the hydrogen. So it's an oxygen with a bond to a carbon that has two methyl groups. Okay, so an oxygen bound to a carbon that has two methyl groups. Oxygen bound to a carbon that has two methyl groups. So when you're using a bigger alcohol like this, you can see how we're just taking the alcohol and popping it on like that. And we've started with an aldehyde, and at the end we still have an acetal. But one of the substituents on the acetal is a hydrogen, and that's okay. You just treat it like you would a ketone. Questions on that one? Okay, cool. So next time we'll talk about nitrogen nucleophiles, we'll talk about the reverse reactions, and then eventually we get to hydrogen and carbon nucleophiles. Yes? This is number 2. Sorry, number 3. Yeah, because we're not forming a ring around the oxygens.
Is there a working
I barely wrote the homework, so even if it was, no.